Uh, we have a quiz tomorrow. I understand that's a popular statement in Course 6 courses this week. Everybody seems to be having a quiz. Welcome to the survivors of the 006 exam. And apparently survivor may be not quite the right word, but you're here, so thank you for coming. So tomorrow's exam is in section. The usual sort of closed book, 50 minutes. If you look at old quiz 2s, you'll probably have a pretty good sense of the sort of things that you might be expected to know. And there's some quiz review videos that have been posted that maybe you'll find useful. Okay, so what we've been working on is figuring out how to compile high-level programs into our beta instruction set. We're sort of doing this one to sort of see how compilation works, but the other thing we're trying to do is make sure that we have everything in the instruction set that we need. I hope one thing that maybe you'll be struck by is that our instruction set is actually very straightforward. There's some arithmetic and Boolean and shift operations, some compares, so the sort of ALU operations, and then there's load, store, and branch. That's sort of it. So it's a pretty simple little machine that we're going to end up building in hardware when we come back from spring break. We've taken care of most things. We know how to do loops using our branches. We know how to access memory with loads and stores in order to get the variable values, like in this case n and r, from memory into the registers so that our arithmetic operations can work on them. One thing we don't know how to do, and that's really the topic for today though, is if we turn things into procedures, and in this case what I've done is sort of rewrite the factorial, the little iterative factorial loop that we had, now into a factorial procedure. We'll want to think about what our conventions are for assembling that. What's the right assembly language sequences the compiler should generate to handle procedure calls and returns and the passing of arguments. And so they're reusable code fragments, and one thing we have to think about is if, particularly in the case of recursive calls of some sort, will we need to start executing another copy of the procedure before we finish executing the first copy of the procedure? And the answer is certainly in recursive procedures. This is not a recursive procedure. In fact, this procedure has no internal procedure calls at all, but many procedures halfway through their execution call another procedure, and we'll want to make sure that our scheme for dealing with procedure calls and returns can handle nested procedure calls and recursive procedure calls, which are just a special case of nested procedure calls. Procedures have a single named entry point, so one of the ways that we encapsulate functionality in a way that makes its reuse much easier is that we come up with a very specific specification for what the function does. You give me one integer argument, as in the case of factorial, and I'll return to you an integer answer that is, then I'll give the expression that my function will compute for you. And we don't typically end up writing code that jumps into the middle of the procedure. We really only expect to use procedures by jumping to the first instruction and passing figuring out how to pass the arguments. We jump to the first instruction, and at some point we expect the procedure to return to us. And procedures are almost always parameterizable, and that's a very fancy word meaning that we tend to pass in some arguments, some values that the procedure will use and will manipulate. So instead of writing a separate procedure for fact of 3 and fact of 2, factorial of 3 and factorial of 2, we actually have one procedure that will offer to compute factorial of n if you'll only tell it what n is. So that's what we mean by parameters. Many procedures have a certain amount of local state. And so in this case we have a local variable r, and by what I mean by local variable is that r doesn't really exist except when you're in the body, when you've made a call to factorial, and then it goes off and creates it figures out what location in memory to use for r, initializes to 1 and things like that. And the thing again that's complicated about this is that if we have nested procedure calls, or in this case recursive procedure calls, you can imagine that because inside of the execution of one factorial there may be other calls to factorial, we'll see that in a second, we realize that at any given moment there might be several copies of R, each one local to the instance of factorial. So factorial of 3, which might end up calling factorial of 2, at a certain point in time, there's sort of 2 copies of R that are around. One for the fact of 3 routine, and a second one that got created when we call fact of 2. So we're going to have to figure out how to make all that work. So a lot of the most straightforward ways of doing procedure calls, of which we'll try one in a second, fail for various reasons, and then we're going to have to come up with a better convention. Okay, and as I say at the end, one of the things that happens with procedures is there's a transfer of control, but there's the expectation that the procedure will return to the caller, and then execution will resume right after the procedure call. So let's do a first try. So here now I actually do have a recursive definition of factorial, where the definition of factorial includes another procedure call, in this case to itself, with an argument that's numerically smaller. And since the argument gets smaller each time, the recursion eventually terminates. And you can see the test for the termination of the recursion. Basically, when n gets to 0, we return 1, no more recursive calls. And you can sort of see that playing out here. In other words, to compute fact of 4, I'm going to have to first compute fact of 3, so forth and so on. Okay. So let's try a very simple set of conventions, and these will actually fail on a variety of fronts, and we'll debug that, and we'll come up with a more sophisticated strategy for compiling procedure calls. But we have lots of registers, so why don't we just use registers? We'll just sort of, always programmers can invent whatever conventions they want, particularly around the use of registers, because they're there for you to use. And you can say, okay, I'm always going to use this register for this and that register for that. So what I'm going to do is to have a convention where I put the argument, in this case, the single argument, into R1. And now you can say, well, what about procedures that take 2 arguments? Well, use R1 and R2. What about procedures that take 17 arguments? How about R1 through R17? What about procedures that take 112 arguments? And then you can sort of see, well, maybe this isn't the best strategy. It was convenient when there's a small number of arguments, but for arbitrary number of arguments, we'll probably have to come up with something more sophisticated. When, let's say you are going to be, you're a big program and you're calling me to do something specific for you. I'm the procedure. So when one of you calls me and says, Chris, could you please compute factorial of 3? I'll need to know which one of you to return the answer to, and then you'll resume execution, right, after I'm done with my job and hand, if you will, the baton back to you. The thing is that we need to have some convention, and not only do I need to know what argument you want me to compute factorial of, you need to give me some information about where to go back to when I'm done. So typically, at a minimum, you need to pass me a return address, a PC that I'll jump to, that I'll put into the program counter, a value I'll put into the program counter when I'm done, which is where execution will resume when the procedure exits. So we're going to put that address into R28, so that's going to be another register that we're going to allocate. So let's take a little list of registers here. So R31 is always 0. So here I'm talking about using R28 to basically always hold the return program counter. And we'll actually give this a special name. It's called the linkage pointer. So it's telling me where I go to after I'm done. Okay, and then finally we're going to have a convention that we're going to use R0 for the return value. So when I compute the actual answer, where do I put it so that you know where to find it? And I'll just stick it in R0. So you'll just assume that when I return control to this program counter, typically almost immediately following, there are some instructions that will use the value in R0 as the result of the procedure call. So here's the compilation that's been done using that convention and some of the techniques we just worked on last time. So here's a procedure call. We're going to move the argument 3 into R1. That was our convention. And then we're going to use the branch instruction, in this case an unconditional branch, this is the destination here, fact. So the next instruction to be executed, so we're going to do the branch, and the next instruction to be executed is going to be that compare less than or equal to constant. So this transfers control from this location in the program to this location, and at the same time remembers the address of the halt instruction in R28. So remember, the branch tests a value. In this case, the BR instruction really is doing a BEQ on R31. BEQ is actually the instruction we have. So it's testing to see if R31 is 0. In fact, it is. So it's going to do the branch. So not only does it transfer control, but in R28 in this case, I'm going to make a little note down here, it puts in the address of the halt instruction. Okay, and it's actually what it puts in is the address of the instruction following the branch. So if you go back and look at what branch does, the thing it sticks into the destination register, this R28, is the address of the following instruction. And you can see why we designed it that way, because we intended branch to be used for procedure call. And we set it up so not only does it transfer control, but at the same time it remembers where execution should resume when the factorial procedure returns. So everybody sort of get the idea here? I'm passing two things in, the argument in R1, and in R28 I have the address in memory of an instruction where I want execution to resume when jump is done. Okay, so now if we go ahead and look inside of the factorial routine, it's going to start using R1 because it was compiled to know that the argument was in R1. That was our convention. So any reference to n, the compiler knows to say, well, that's going to be in R1. I'll just go ahead and use that. So it tests to see if it's 0. And if it's true, it goes down here, where it's going to move a 1 in, and I'll talk about the jump in just a second. Here's a recursive call, and remember our convention, so n minus 1, so well, up here I've moved R1 into R2 to save away a copy of n, because I need to make a recursive call which is going to reuse R1, but notice I need to use n after the recursive call returns. So as the assembly language programmer, the compiler has to say, wait, I need n, so I'm going to save myself a copy of it, and then compute n minus 1 in R1 and do that recursive call. Okay, so I'm following the same calling conventions to make that second call to factorial, that nested call to factorial. And when I come back, I'll go ahead and take the result that came back in R0, and I will multiply it by the saved value of R2, which is the value of n. So that would be n times factorial of n minus 1. That's what that multiplication is doing, because factorial of n minus 1 will be in R0 when the procedure call returns, and R2 is where I saved my copy of n. And then finally, I come along here, and this jump instruction, the one instruction I didn't describe to you before is I can say jump, and then typically give a name of a register. Okay, this one actually. Jump is like branch in the sense that it saves the address of the next instruction into that destination register, but R31 means we're just throwing it away. But what jump does is to take the value of that register and stick it in the PC. So this takes the contents of reg RA, in this case R28, and simply sticks it into the program counter. So there's nothing conditional about it. It's not testing any values. It just says, take this number and stick it in the program counter. And the number I want to stick in the program counter is the value I passed in R28. So that's where I wanted execution to resume. There's a couple flies in our ointment here. Okay, so notice that when we did the recursive call, we actually replaced this address that was in R28. And what address did we put into R28 instead? Right, we actually put in the address of that multiply, which was the instruction that followed this branch. And that was, we're all following our convention here, but now you can see there's some bogosities in our convention. What was the problem? The problem is that we've been reused R28 in the middle of the procedure, and in so doing, we wiped out where we're supposed to return to. Right, so that's one thing. The other thing is, notice about R2 here. What I've done is I've carefully saved a value into R2, hoping it will be there after I make my recursive call. Right? I mean, you can see I carefully put something in R2 here, and then I expect it to be there after the recursive call. Will it be? Yeah, when I called factorial, it said, wait, I get to use R2. And you're saying, no, I'm using R2. And then you say, wait, we're the same guy. You know, we have to make up our mind collectively here to sort of figure out that we have to have a convention about registers. And there's sort of two obvious conventions. One is that when you call me to do something, I can use any register I want, which means, and then you can't rely on the value of any register, which means you can never leave anything in the registers that you expect to find there when the call returns. Or the other convention is that I can't use any register but R0. I mean, R0 is already known to be changing, but any other register that I want to use, I have to save its value, then I can use the register, then I put back the old value I was. So there's a sort of notion of, can you rely on the register contents being the same or not? So that's a convention we're going to have to decide on. Okay, this convention here of assuming that I can use the registers but then not saving their values just means that register values will disappear on me when I make procedure calls. So this procedure here clearly, this compiler here was clearly a little confused over, can I expect R2 to be there or not? And it was inconsistent. It expected it, but then it didn't produce code that actually made that expectation true. Okay. So we pointed out the R28 problem, we have the R2 problem. So this convention, although maybe simple, and it gets the basics, you can sort of see all the things we'll have to keep track of, although simple, we're not getting all the job done we want to. So we're going to do a more careful job of figuring out everything we need to save away, and when we do procedure calls, we're going to try to solve all these problems and come up with a nice airtight convention we're going to use. And it's actually reasonably straightforward, but there are a lot of details to take care of. So that straightforward does not necessarily mean simple in the sense of I can tell it to you in one sentence. We're actually going to have a bunch of conventions. And in a couple slides, I'll lay them out for you explicitly. But just to make our little laundry list, right, we need to have some way of passing arguments. And 1 argument, 2 arguments, 17 arguments, 22 arguments. Most languages allow procedures to have as many arguments as you want. And some languages even allow procedures to have variable numbers of arguments. Like printf in C, you can pass in a simple string or a string with lots of other values. And the number of values that you pass in, you can write 3 values to be printed by a printf or 17 values. It all depends what the format string is. Right? So we're going to have to figure out a convention for passing arguments that doesn't, key on if you only have at most 5. We're going to have to allow more than 5. A convention for the return address and a convention for returning the results back to the caller. Notice, by the way, that in most languages you can put an expression in for an argument. So here I'm calling the function sign on a plus b. The expectation is the compiler will compute the value of a plus b and then pass the result of the sum. It's not actually passing little pieces of code in. It's just the code there is just a way of telling the compiler, compute this expression, and the value of that expression is what gets passed in as an argument. Inside the procedure, we may have complicated expressions. And in fact, if there's a nested procedure call, we may have to save a computation that we're halfway through, the temporary result. We may have to save it somewhere. We may have local variables, and we haven't talked really at all about, if we have a local variable, where should that go? But we'll solve all these problems in a second. The point I'm trying to make is when I do a procedure call, there's a whole list of storage requirements that I need. Places to put the arguments, places to remember where I'm supposed to go to when I'm done executing the procedure, places for temporary results, places for local variables. Altogether, I can make a long laundry list of everything Factorial will need to be, to get its job done. And collectively, we're going to call these an activation record. It's a collection of storage that we need. Every time I make a call to Factorial, this storage has to be put somewhere. Okay. And in fact, when I make a call to Factorial, for instance, fact of 3, you can see that somewhere along the way, it will make a recursive call to fact of 2. And fact of 2 has that same laundry list of things it needs to save, all of which will be different than the values that are being saved for fact of 3. So there's sort of this notion of this accumulation of these activation records. Right? As I continue my calls, I'm getting more and more and more activation records sort of being stacked up somewhere. And I use the word stack very carefully because that will give us, it gives us a hint about the data structure we're going to use to hold those activation records. And then finally, when I start returning, when I'm finally done with the procedure, I stick the answer into R0, and then what I'm going to do is I can get rid of that activation record. I'm done. Fact of 0 is done now. Fact of 0 has finished its job completely. It's put its answer into R0. That's the residue of its life. And now we take the corpse and we can say, okay, all that other storage, that, the temporary variables, the local variables, you're done. Those can be recycled. We can return those to, ashes to ashes. So once we exit that procedure call, we no longer need its activation record. And in fact, if you look carefully about when activation records are created and destroyed, they follow a very simple discipline. Every time you make a nested procedure call, you add a new activation record, but then you have to return from the nested procedure calls in the same order that you called them. So you might do call, 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 return, return, call, return, call, return. But you can sort of see that at any moment when we return, we get rid of the topmost activation record in the stack of activation records that we have. So imagine each one of these books records all the information that we want for a particular invocation of a procedure. Its argument, where to return to, any local variables that are just for that procedure call. Those are all written in pages of each one of these volumes. And every time we do another nested procedure call, we need to add new activation records. And so this notion that this is sort of a last in, first out data structure. If it helps you to think of it this way, think of it as a napkin holder. You can stuff napkins into the top and you can take them out one by one, but we're always ever dealing with, if you will, the top napkin. Okay. And at some point I start returning, and what we're seeing now is the stack is going down. So the stack is a data structure, and in fact, all of your laptops, every procedure that runs has its own stack, and all the compiled languages, C and Java and Python, or I don't mean compile, all the languages which implement procedure calls all have this notion of an activation record that's created for each procedure call, and it stores those activations in a last in, first out data structure that we call the stack. Okay, so now we're going to have some conventions here. I'm going to allocate R29 for this as the stack pointer. So let me say a little bit about what a stack looks like. A stack is just a big array in memory. So here's my memory, and I'm going to put my low addresses down here. And this is going to think of it as a stack of words. So these are consecutive words in memory where the addresses are growing up. Now, it may bother some of you that when I said up, I drew a down arrow. And I just have to tell you, I'm very sorry, but generations of computer scientists have always written low addresses at the top of the board and high addresses at the bottom of the board. So up in addresses is down in gravity. So what can I say? So you can see our little screen beam here is puzzling over how up became down. But just so that you're clear, this stack is growing up in addresses, and we always draw that, sadly, down the board. Okay, so R29 is going to tell me what the next location in the stack that can be used is. So locations that are below whatever by R29, I mean, if I looked in R29, I would find a number, and that number is the address of this location. Just to be clear what I meant there. And all of these locations here, which have addresses that are below the number in R29, okay, are locations that have already been used on the stack. If I want to use a location on the stack, I can. All of these guys are free. So these are used. And these are, or maybe free is a bad word, available. They're free for you to use. They're ready for you to use. Okay, and the convention is you can put something on the stack at any time. Any fragment of code can suddenly put something on the stack, but it has to remember to take it off again when it's done. Because the expectation is at any moment that, that if you put something on, it's up to you to take it off. If you leave it on, you're going to confuse other people who expect to find their thing at the top of the stack, because last they knew, that's where it was. So the convention is, you're running, you put some things on the stack, I'm running, I put some things on the stack. When I'm done, I have to take them off again before you get control back. because I want to make sure the stack is just the way you left it. Right? So there's a sort of this convention about that we're going to follow in our course that's often followed, is that my job is to leave pretty much things exactly the way I found them. My job as the procedure is to leave things exactly the way I found them before I return to you. So you should expect everything to be just the way it was when you called me, except for R0, whose value is going to change. Yes, sir?
How do you guarantee that arguments you've already have stored in the register while you don't actually fill up the stack and start overwriting?
Well, what you're worried about, if I keep using the stack, am I going to run out of stack? And that happens in real life. I mean, if you go off and write a Python procedure that does a recursion depth of, say, 300, you'll get an error from the Python execution system saying, wait, I'm out of stack. And so you can run Python with a bigger stack. Most operating systems have a way of adding additional storage, not in terms of moving the addresses, but it says, look, I'm going to give you 500 locations of stack, and then you use more than that. It says, fine, I'll give you another 500 locations. It's sort of like making a disk file bigger and bigger and bigger.
Where are those stacks?
Where are those locations? Well, memory is big. We have, how big is our address space in the beta? How big is our addresses, our memory addresses in beta? 2 to the 32, so that's 4 billion bytes, okay, or 1 billion words. Right, so if you need more than that, you probably can't run on a 32-bit machine, sorry. 64 bits gives you a bit more than that to work with. And later on we'll talk about memory layouts. So there's some issues there, but for now let's just assume that we've arranged for there's plenty of room to do the activation records we want to store. Okay. So we're going to use software conventions. Notice the only thing we've really done is to allocate one of our registers to be the stack pointer. But that just means we're going to use that. There's nothing special about the hardware. R29 is just like R27 and R28. Okay. All we're doing is just setting this aside, and the compiler will follow the convention that whenever it wants to put things on and off the stack, it will use the R29 register to remember what locations have been used and what locations are available. So here's a bunch of little macros that we've written using our macro capability from last lecture that actually expand, okay, into little sequences of instructions, of beta instructions. So if I want to push something onto the stack, what's the convention? Well, first I have to sort of give that stack location to myself. So what I'm going to do is to take the stack pointer, which was pointing to here, and add 4 to it. So now the stack pointer points down to here, and I've allocated myself now this word to use, this word right here. The one that used to be at the top of the stack, I've moved the top of the stack down 1, and now I can go ahead and fill up this guy with whatever value I want. So you can see there's an add that moves the stack pointer higher into a higher address, allocating this memory location. Now I can move something into it with that store instruction. Pop does the opposite. It takes whatever was at the top, it takes this word, puts it in a register, and then moves the stack pointer down 1. And so what we have is sort of a push and pop are the opposite of each other. Push takes a register value and puts it onto the stack, and pop takes something that's on the stack and puts it back, puts it into a register, and both of them either make the stack pointer go up in memory or down in memory. Everybody sort of happy. So just think of this as a big array, and we're just sort of using the end of it to push and pop information. Yes, sir?
So with our stack, are we still moving the L13 R28?
We haven't talked yet about, I'm setting up this data structure, and now I'm about ready to show you what we're going to do in terms of actually procedure call and return. So that's a great question, and I just want to finish. We have ways of allocating a bunch of words on the stack at the same time, just moving the stack pointer by a whole bunch, or deallocating the same bunch of words. These orders, the order of this addc in the store and the order of this load and this addc, are carefully chosen. Now, we don't quite have enough information to understand why the order of those two instructions is very important. but I'll give you just a 10-second hint. What happens here is we're very careful to move the stack pointer, to allocate the location before using it. Suppose I did it the other way around. I used it and then I moved the stack pointer. Well, you could say, well, if those two instructions are one right after the other, would it really matter? I mean, I'd use a different offset on the store because I haven't manipulated the SP instruction yet. Would it really matter? And the answer is yes, if somehow the execution of the sequence of instructions was interrupted between this instruction and that instruction. If they were in the opposite order, I would have put something on the stack, but because I haven't changed the stack pointer, that location would still appear to be free by our convention that SP points to the first unused location. And we haven't talked about interrupts and the notion of suddenly stopping execution between any two instructions and going to do something else, but we'll get there. Meanwhile, we carefully arranged these macros to be in the correct, to have the instructions in the correct order, that we're always following stack discipline. We always allocate a location before we use it, and then on the pop, we always finish using it before we deallocate it. Okay. So stacks are pretty good. I mean, if we're running along and we suddenly have to do this exciting little program. This, by the way, is a capsule summary of about 1/2 of the Star Trek plots, which seem to involve some crisis involving dilithium crystals, which lasts for an entire hour, and then disaster is averted just after the last commercial. So, but the notion is, I have a fragment of code here that needs to use R0 and R1. I don't know whether R0 and R1 are being used anywhere else in the program, but I don't care because I can save their old values. Those two pushes put R0 and R1 on the stack. I can now go ahead and use them because I've saved away the values that were in them. And when I'm done, I pop them back out, right? So everybody's happy. Whatever the value, when I'm done, whatever was in R0 and R1 is now back in it, even though I've borrowed them temporarily for a set of instructions. And notice that the push and pops happen in opposite order. I pushed R0, I pushed R1, and then when I pop them, because now the stack pointer is here, when I pop them, I'm going to basically pop in reverse order. And that's what the last in, first out discipline is sort of all about. Okay, so this is, a long little slide full of bookkeeping. What I recommend we do is just focus on the use of these three registers. So I'm going to rewrite my little list of registers here to be slightly more coherent, to remind us what we're doing. So we're going to have R30, the magic R30, which you've been carefully avoiding, and will continue to avoid for about 2 more weeks. But meanwhile, don't use R30. You'll see why. But then there's R29. What was R29 in our convention? That's the thing that's keeping track of where we are in the stack. So that's the stack pointer. R28, what was R28 going to be in our convention? That's what the return address goes into, right? So that's going to be what we call the linkage pointer. So these are just nicknames for these particular registers. And then we're going to have one more register that we allocate called the base of frame pointer. And say, well, how many pointers do we need, Chris? Well, we'll need these three things here, and then along with R0, which is sort of the return value. So these are all the conventions that the registers that we'll use to implement our procedure call and return conventions. And you can say to yourself, well, Chris, what have we done? You've taken care of where the return value goes, and you've taken care of keeping track of where I have to return to once I'm done execution. The procedure is done execution. Okay. You haven't talked to me about arguments yet and things like that. So we're about ready to do that. Okay. So here's our little scheme. What we're going to do is we're going to push the arguments onto the stack. So we're going to use the stack to pass all the arguments in. And what's the advantage of putting the arguments on the stack? Well, we can put as many as we want on, right? We're not going to suddenly run out of registers by saying if they go in registers, you can have at most 26 arguments, and after that, sorry. We can put as many arguments as you want. Okay, and then we're going to, once we have the arguments, and now we start executing in the procedure, you'll see that we're going to put a bunch of other information onto the stack as well. So we're going to save, the first thing the procedure is going to do is to save away the value of the LP register. because it knows that at the end of the procedure it will need it. Why would it save it away? Remember what the problem was in our bogus example early on? If there are any nested procedure calls, they will want to use the linkage pointer as they transfer control to the nested procedure. So in order to free up the linkage pointer for use inside the procedure, we first go ahead and carefully save it away. And some compilers are very optimized out the wazoo, and they notice if there are no nested procedure calls, there's no reason to save the linkage pointer. But we're going to be dumb. We're going to have these little template-based things that know nothing about the insides of the procedure. We're just going to assume we always need to save away the return address because it might be overwritten if there's a nested procedure call. We're going to save away this base of frame pointer. So there's a value that comes in, and you'll see why in just a second. Because the next thing I'm going to do, so I'm carefully building up this picture of a stack, right? So you see a detailed picture on the slide, but if I just think about this, think of this as my stack of books, right? So here's one book, and here's my next book, which is some number of locations on the stack. What I'm going to do is the base of frame pointer is a pointer, if you will, to the current book. And so when I got called, I had a pointer, if you're calling me, the base of frame pointer pointed to your book, your activation record. And what I want to do is when I'm done building my activation record, I want to use the base of frame pointer to point to me. So I save away the pointer to your activation record, and I will restore it before I return to you. Okay, and then finally, there are other things so I've carefully got the arguments here, and then the safe value of LP and BP. And then the other things I'm going to put in here are any temporary and local values that I need. Any registers that I need to save will go on the stack. Those are all the things that appear in a particular activation record. Okay, so you can see that what we're doing, we don't really need the base of frame pointer. It turns out we can do everything off of SP, but it's just convenient for lots of reasons to just have a single pointer that always points to the same location within the book. And we'll see how that works in just a second. So here's our details here. Yes?
So BP, what exactly is that?
BP will be the address of a particular location in the activation record.
Which particular?
Well, I'm about ready to tell you exactly which location it is. Okay, it's this location here. Okay, so the caller will put all the arguments onto the stack. Then I'm going to save away the LP and BP registers. Okay, remember that old BP pointed back to the book from the activation record of the caller. That's the moment. And then we'll set up the BP here in my frame. I'm always going to set up BP to point to exactly that location. The location in the activation record, which is just below where I saved the previous BP. That's just a convention. It could point to other exact locations. The advantage of choosing this one, as we'll see, is that the arguments will be a fixed distance from the base of frame pointer, and all the local variables will also be a fixed distance from the base of frame pointer. So it's just think of it as like a data structure. I have a pointer to the data structure, and I've just happened to set it up to go this way. I really can't change BP until after I've saved the old one. That's sort of the earliest moment I can go ahead and put a new value into BP after I've saved the old value of BP. Okay, the arguments are pushed on in reverse order. Anybody know why I push them on in reverse order? Notice if I call f of 1, 2, 3, 4, first I put 4 on the stack, and then I put 3 on the stack. Why am I putting them on in the reverse order? Yes, sir?
Because your BP is below your arguments, you're going to be going
Right, but you can imagine that, at least in theory, arg0 could be first, and the last argument, it would still be a fixed distance away, but you're definitely on the right track. It has sort of to do with a convention I talked about earlier of passing variable numbers of arguments. Right, so here the first argument is always a fixed offset from the base of frame pointer. If I push it on last, it'll always be exactly two words above where the base of frame pointer points. Right, and so if you think about how something like printf works, it's the first argument gives you all the information you need to know how many other arguments there are going to be. There's a var args, thing you can do in C, and so which sets up the procedure so you can actually ask the procedure how the procedure can ask how many arguments did I get this time, and all of that really depends on being able to get to the first argument without knowing how many arguments there are altogether, because the first argument will tell you, and if you can't get to the first argument, well, you're sort of screwed. So we put the arguments on in reverse order. Okay, so remember, if you're evaluating the arguments in reverse order, any side effects that happen on the last argument will actually happen before any side effects of evaluating the first argument, something that people sometimes, go, oh, I never knew. So hopefully you're not hiding side effects inside the evaluation of expressions, but sometimes people do crazy things. Okay, so we push them in reverse order so that we can always get at the using a fixed offset from BP. In fact, it's going to be minus 12 off of BP. Whatever the BP, the address of whatever, the number in BP is the address of this memory location. If I subtract 12 from that, I'll have the address of the first argument. Okay, so in assembly language, if I wrote something like minus 12, well, if I wrote load BP, comma, minus 12 into R0, that's going to take the contents of BP, subtract the constant 12 from it to compute. So this is, well, that together, the addition of the value of the BP register and the minus 12 is that addition, which is what the load instruction does for me, gives me that address, and it's the contents of that address that get loaded into R0. So this would be the assembly language statement I would use to actually get the value of the first argument. And then if there's any local variables, I just use a big allocate statement to leave room for them on the stack, and they'll be at positive offsets. So this is not, I mean, you can say, couldn't I have had a different convention? Absolutely, you could. But we need a convention. I'm describing one here. Others are possible. Yes, sir?
So I think I understood everything up until the point with BP.
Yep.
Putting it in a certain order that it's put in allows you to have variable amount of arguments.
Oh, so what you want to know is why does putting the arguments here in reverse order allow me to have a variable number of arguments? The answer is that typically when I have a variable number of arguments, something like the first argument will tell me how many other arguments there are. If I put them in the other way, I wouldn't know where that first argument was because it would be, I'd have to know how long everybody was. Right? By putting it this way, the first argument is always in the same location relative to BP. And I can look at it and say, oh, now I know how many arguments there are.
What exactly does BP do?
BP is just the address of a particular, it's like, I've got this activation record, it's a data structure. BP is essentially a pointer to our data structure. Right? It lets me go access the arguments and the local variables and the saved values of BP and LP in that area. So all the the way we'll use BP is always with negative offsets for the arguments and positive offsets for the local variable. But that's how the compiler will access all that activation record information, by making relative accesses to BP. Okay. So here's our contract. This is the convention we're going to follow. We're going to push the arguments onto the stack, and when you call me, you'll put the return address, where you want me to return, into the linkage pointer. Okay. And since you put the arguments onto the stack, when I return to you, it's going to be your job to take them off the stack. So we have this convention that whoever puts something on the stack is responsible for taking it off, because they know exactly how many things they put on the stack. So they'll take exactly that many things off. So the caller puts things on the stack, calls, leaving the return address in R28, and then when the procedure call returns, the first thing it does is to take all the arguments off the stack, and now everything is back where it was, except I now have the answer from the procedure in R0. The callee, in other words, the procedure that you're calling, okay, I'll do the computation, leaving the answer in R0. When I'm done, I'll take that return address you gave me, and I'll put that in the PC, and that'll be the next instruction to be executed, or the address of the next instruction to be executed. I'll leave the stack just the way I found it. Anything I put on, I'll have taken off. Anything that you put on is going to be your job to take off. And then I'm going to leave all the registers exactly as they are, except for R0. So here's the actual little entry calling sequence. So push, 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 put the arguments, do a branch, leaving the return address of the deallocate macro here, this instruction here, into LP. When the procedure call returns, this pops off the n words that I put onto the stack. Instead of doing pop, 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 since I don't really want their values, popping puts a value into a register. Since I don't want their values, I just say, just get rid of them all. Bulk disposal without really caring about what the contents are. Entry sequence, I save the LP and BP registers. I make a copy now of the stack pointer, and that will become the pointer to the activation record of the current procedure. I go ahead and allocate other variables and save any registers that I want. And then to leave the procedure, I basically undo all of these things. So you can see each one of these guys here is really the opposite of what happened there, in the opposite order. Right? So if I push R1, R2, R3 on the stack, I pop them off, R3, R2, R1. And so this is really just undoing in the reverse order everything I did here to build the record. I'm now unbuilding it. Yes, ma'am?
So allocate just doesn't put things in, it just says I'm going to use these.
Right, so when you have something that says int x, int y, int z as a local variable inside your procedure, right? The compiler just allocates room for them. Then it's up to you to write statements that actually initialize them to 0 and 1 and 17.
But if you then want to use that allocated space, the way you put things on the stack is you push it, and that will give them...
No, so this allocate is actually moved the stack pointer. So those words are now safely allocated. Now you just use regular loads and stores to put values in and out. Push is when you want to sort of both allocate and initialize at the same time. Allocate just says, leave me room, and I'll use loads and stores to fill it up. Okay, and notice we don't really need an explicit deallocate because this move of the base of frame pointer back to the SP, so the SP may be all the way up here, this move of the base of frame pointer to the SP sets it back. So that move is an implicit deallocate. Okay, so here's our favorite procedure, all carefully, you're going to get pretty tired of factorial, but all carefully written out. This was compiled using our compilation conventions, and you can see the entry sequence and the exit sequence, and in fact, okay, there's the entry sequence. Why did we push R1? Because notice this code down here uses R1, and because I have to return the registers in the condition I found them, the fact procedure, have to save away the old value of R1 so I can use it for whatever I want, and then before I return down here, notice that I will restore it. Right, so there's the entry, and here's the actual little calling sequence. Push the argument on the stack, do a branch, do a deallocate. Okay, so you should be able to use the calling convention, those little templates that I talked about, and understand the sequence of operations. Recursion, there's actually nothing very fancy about recursion. Okay, it's just like nested procedure calls. The fact that you're calling the procedure again with a different argument doesn't change in any way whatsoever how the stack frames are built. So you can see the activation records slowly be building up and being pushed on, being built onto the stack in last in, first out order. Okay, and they're deallocated in reverse order. If you think about it, if I stop the execution of this program, sort of at this point with all these records on the stack, you actually can deduce a lot of information about what's exactly happening. And in fact, when you have an error in your program, like you make a bug in your Python thing, you see a little backtrace. Well, you called foo, and foo was called by bar, and bar was called by, blech, and you have this long list of all the procedure calls that you were in the middle of and what their arguments were. All that information is information that can be found in the stacked activation records. And Python is just happily printing them out for you, so you can sort of say, oh, at least I know what I was trying to do. I don't have to go figure out the bug. Okay, so this next slide here is an example of there's a bunch of questions and there's a bunch of deductions that we're making from the stack frame. You should look at that slide and try to understand how this sort of stack detective process is working. And in fact, what I'll encourage you to do, you'll go over this a lot in recitation. Sadly, not tomorrow, because you have a different task in tomorrow's recitation. But right after spring break, you'll sit down and you'll start looking at how to look at these stacks. So you've got lots of practice building up stack frames and understanding what they mean. And this is sort of an example of that here. All these different questions we can answer. Okay, so just in my last minute, some languages allow first-class procedures. You can actually return a procedure as your answer, not only a numeric value, but can return a procedure. If those procedures contain free variables, for instance, here's a procedure here I'm returning. So if I call f, I get back a little anonymous procedure that adds the argument to f plus the argument to the anonymous procedure together. The trouble is that if you're relying on some information in activation records that's going to go away, that's a problem. And we'd have to do something much more sophisticated than what we're doing now to build the appropriate closures. And that's sort of a topic beyond our course. A lot of what languages do to avoid this problem of remembering information in activation records that might go away is they disallow the notion of procedures as first-class citizens. So for example, C, you can't have first-class citizens. You can't build procedures with free variables in them and expect everything to work like you find it to work in Python, or in Java for that matter. Okay, a little talk about dangling references that you'll cover in recitation. So what I want to do is just point out that there's a variety of different conventions we can use. Sometimes the languages are pretty loosey-goosey. They just let whatever happen, happen, and if you do something stupid, like try to look at a location in an activation record that's no longer there, well, that's your problem. Other languages like Python and Java think that's a bad idea, so they disallow language constructs that would let you do that. So this whole notion of, is a language, safe or not, that's often a discussion about the conventions it uses and what it will allow you to do relative to the activation records. So I'm going to stop there. I hope everybody has a good spring break. And when we come back, we get to start actually going back to hardware and building the hardware, the circuit, that will implement this instruction set. So good luck on the quiz, and have a good break. We'll hope it's better than 6006.